So I'm going to be talking about basically fast low-rank approximation methods beyond randomized matrix sketching. All right, so the first thing I want to talk about is just why study low-rank approximation and principal component analysis. So the obvious answer to that is these are two like super widely used primitives in machine learning and data analysis. They're used all over the place. But in the vanilla setting, they're both basically solved by doing a singular value decomposition. And this is something that has been studied in the numerical linear algebra community for decades. There's lots of really well-developed implementations. There's lots of really well-developed theory. So why am I still studying this problem? Why do I still think it's interesting? There's a couple reasons for this. Number one is sort of the obvious, just that we're working on different types of data sets. Not only are they larger, they're not always larger, but they also, for example, are much less structured. So there's tons of work on speeding up SVD algorithms for structured matrices. And obviously, there's a lot of SVD algorithms that don't take into account structure, but there's maybe less work that could be done for dealing with unstructured matrices. There's sort of new parameter regimes. You're computing different numbers of singular vectors. And one of the most important parameters is error. So error parameters are also changing. There's new accuracy measurements for new applications. And there's sort of two reasons there's new accuracy metrics. Basically, like, there's this intuition that in machine learning and in data analysis, generally you set your error, your epsilon, to be much greater than machine precision. So you're willing to tolerate basically larger error tolerances, and then you can look at different types of algorithms that give you these sorts of error tolerances. But it's not just that you're willing to tolerate larger error, there's just different ways of measuring error. So if you're computing an eigenvector for some sort of scientific simulation, that eigenvector might have a physical meaning, and you want to somehow actually approximate that eigenvector. If you're computing an eigenvector because you're using it as a principal component, there's no real physical meaning. It's sort of like, it's a tool for visualization or for classification or something like that. And so you should be measuring what is a good principal component using a different type of error metric than is traditionally studied. It's not just that epsilon is bigger, like epsilon should be different, basically. And then the final thing is new tools. So the thing that I look at most probably is randomized methods. So the biggest thing something that I work on a lot, and some people here work on a lot, is basically randomized sketching, which is basically I have a large data set. I want to do a low-rank approximation or a principal component analysis of this data set. I choose some random matrix independent of my data set. I multiply it by my data set, and I get this sort of randomized compression. And from this compression, I can still extract enough information to do some sort of reasonable data analysis. So this is one really widely used randomized tool that I'll talk about in a bit. And then another randomized tool, which is not really new, but there's been a lot of interest and a lot of results recently, are basically on stochastic optimization methods and stochastic gradient descent methods. So these are basically you're doing optimization via gradient descent, but you're saving time by not computing full gradients at each step. And there's lots of really interesting bounds here. They actually can give, like, for example, if you're solving linear systems using these methods, you can get just different bounds than you would get with traditional, like, polynomial-based solvers. So I think there's tons of work to be done here. So these are two methods I'll talk about a bit. Okay, so I guess like the main point of this talk, which I hope I'll get across, is that I think that even though low-rank approximation and PCA are super well studied, there's still a lot of room for cross-fertilization between what's known in numerical linear algebra and what people are doing in machine learning and data analysis. And I'm going to basically try to give like a couple examples of this in the talk. I think basically not everything has been solved on these problems, but at the same time, there's a lot of stuff that's been done in numerical linear algebra that can be ported over to data analysis and machine learning and can give a lot of new understanding. Okay, so first example, I'm going to talk about this paper from NIPS of last year with Chris Musco on randomized block Krylov methods for approximate singular value decomposition. So let me try to give you background on the singular value decomposition. Probably a lot of people have seen it, but I don't know if everybody has seen it. Oh, wait, actually, sorry. So what this is going to combine, if you forget everything I said about this, I'm trying to combine randomized sketching methods, which have been really big in the theoretical computer science area, and I'm trying to combine these with basically like traditional Krylov subspace methods, and showing that by combining these methods, I can do better. We can get sort of better bounds for low-rank approximation. That's the high level of what this paper is trying to do. So what is the SVD? It's something I can apply to any matrix. I take any matrix A, and I can decompose it into the product of three matrices. Basically, U has orthonormal columns, which are the left singular vectors of the matrix. They span its column span. V it has orthonormal rows. They're the right singular vectors of the matrix. And then sigma is a diagonal matrix. It's non-negative, and it contains the singular values of the matrix, usually basically ordered from sigma 1, which is the largest, to sigma d. Now this is principal component analysis. The singular vectors are the principal components of the matrix. And so this is why this is very useful. Those principal components corresponding to larger singular values are the important principal components. They're sort of the directions of largest variance within your data set. Also, you can directly read off optimal low rank approximations from the SVD. So if I just take my matrix and I basically zero out all but the top k principal directions, I get this rank k matrix AK, which is the best k rank approximation of my matrix in many senses. One sense is that if I look over all rank k matrices B, it minimizes the Frobenius norm distance between A and the rank k matrix B. So it's optimal in the Frobenius norm reconstruction sense of doing low rank approximation. Another norm that it's optimal in is the operator norm. So this is an important norm for low rank approximation. So if I compute an SVD, not only is it giving me the top principal components of the matrix, I can just read off an optimal low rank approximation, and then I can plug in this low rank approximation to whatever application I'm using it in. Let me just mention that the zeroing out of singular vectors is not always the way that people talk about this. It's also equivalent to projecting onto the span of my top k principal components. Doing a full SVD, though, requires ND squared time, so it's just totally, you can't do a full SVD for a large data set. It's like solving a linear system with Gaussian elimination. It's just not, so you have to do something different, basically. And the traditional solution is iterative methods. So traditionally, if you're doing SVDs on large matrices, you're using some sort of iterative method. You're just going to compute like k singular vectors of your matrix or k principal components instead of a full SVD, and that's all you need for low rank approximation or PCA. The runtime is typically like the cost of an iteration, which there's lots of different iterative methods, so I'm just being rough, is something like doing k matrix vector multiplies. So n and za, the number of non-zeros in your matrix, times k. And then whatever your iteration count, which will depend on your error and your convergence rate and all sorts of things. But typically this is much smaller than the cost of a full SVD. And the two iterative methods that like most things are based off are basically the power method. So probably a lot of people have seen power method for example, computing the top eigenvector of a matrix. And then the Krylov and Lanczos methods, which are basically accelerated polynomial methods and sort of actually like the focus of what this work will be focused on. Okay, so what sort of guarantees do these iterative techniques give you? First of all, you're looking for some top singular vectors of your matrix. And the sort of guarantees that they're going to give you are basically, if I compute an approximate singular vector like u tilde I, and I want to basically prove that it's going to be close to my true singular vector ui in some reasonable norm like the 2 norm. And the runtime ends up being something like the cost per iteration, which is this n and zak term, and the number of iterations basically has this logarithmic term, which is because you're basically getting linear convergence on your error, and then it also depends on your convergence rate. And critically, this convergence rate depends on the spectrum of your matrix. So it depends on whatever your input matrix is. Specifically, this is an example just for like power method, which is the most basic iterative method, but this sort of generally applies, this sort of principle that you're going to depend on the spectrum of your matrix. If you want to get convergence and that sort of error guarantee, you're going to depend on what's called the spectral gap. So probably a lot of people have seen this with like Markov chain mixing or just because you've looked at SVDs and eigenvector decompositions. It's basically the relative gap between your kth and your k plus first singular value. If this gap is small, those singular values are very close to each other, and it's difficult for iterative methods to distinguish between the two singular directions. So basically, the smaller the gap is, the more costly the iterative method becomes. And it's sort of inherent, so sometimes it's just sort of included and thought of like a constant in a way, as it depends on the convergence rate, but it can often be the dominant factor in the runtime bound. Because often gaps actually are very small, especially in data analysis applications where you're not going all the way down to machine precision, so your epsilon is not necessarily all that small. Okay, so how do we remove this dependence on the spectrum of the matrix? A modern solution, which is like there's been tons of work on in the last maybe 15 years, is randomized sketching, which I mentioned briefly. You have your original matrix A, you multiply it by a randomly chosen sketching matrix pi, and you produce this sort of randomized compression of the matrix. And depending on the distribution of pi, you can basically prove things about this sketch A tilde. Specifically, you can prove you can extract good principal components from it. So one thing you can get is basically you can get some principal components u tilde k, such that if you project onto them, so A minus u tilde k transpose A, this is A minus its projection onto the principal components of essentially A tilde. So you essentially worked with a sketch instead of the original matrix. This Frobenius norm error is within 1 plus epsilon of the optimal for Frobenius norm error. And you can get super fast runtime. So the dominant cost in the runtime is something like the number of non-zeros in your matrix. This is basically the time to multiply your matrix by this random sketching matrix. The sketching matrices are chosen so they're fast to multiply by, so specifically either structured or extremely sparse. So that's the dominant cost in your runtime, which is super fast. That's basically the time to read your matrix. Okay, but let's talk a minute about, so you get really good runtime bounds. What is the deal with this Frobenius norm error guarantee? So this is one way of talking about a good low-rank approximation. You've gotten a low-rank approximation which is near optimal in the Frobenius norm metric. First of all, it's totally different than classical bounds on the SVD. So classical bounds on SVD algorithms are telling you actually computed good singular vectors. You don't need to have computed singular vectors close to the true ones to get a good low-rank approximation. If there are two singular values that are close to each other, you don't really care about distinguishing them. You really just need to get one or the other. Second of all, it's sufficient in many circumstances, both like intuitively speaking, it's nice to get something close in Frobenius norm. You can also prove sometimes it's sufficient, like for various clustering tasks and stuff like this. So it's a really useful error metric, and it's nice that we have really fast algorithms for it, basically. But it can be weak. The reason it can be weak is basically the Frobenius norm of a matrix. So the Frobenius norm of a matrix is the sum of its squared entries. This happens to be equal to the sum of its squared singular values, or the sum of its squared eigenvalues. If you look at the Frobenius norm of A minus its best rank K approximation, the best rank K approximation basically zeroes out the top K singular values of the matrix. So this Frobenius norm is the sum of the bottom eigenvalues of the matrix, all but the top K. Most matrices display like what you call spectral decay, which is basically that the larger singular values tend to be significantly larger than the smaller singular values. Like almost all data sets have this, and this is why low-rank approximation is such a widely used tool, because basically the data set is in some sense close to low rank. But despite the fact that you have strong singular value decay, if you have a really high dimensional data set, and if your decay is not super strong, this sum of small singular values can actually be very large. So basically, I call this like a heavy tail of singular values. Even though there's a lot of decay, and even though this is a matrix you might care about doing a low-rank approximation for, this Frobenius norm error is very large. So it's another way of saying it is that this matrix doesn't have a good Frobenius norm low-rank approximation. Often the size of the tail can be bigger than even the largest singular values of the matrix. So there are cases when the Frobenius norm guarantee doesn't really give you any sort of guarantee on the quality of the low-rank approximation, even on matrices that you actually care about low-rank approximating. Okay, so we want to solve this problem. That's what we set out to do is like, well, what if we want to still have a really fast runtime? We don't want to depend on the spectrum of the matrix, but we want to do better than Frobenius norm in cases when it's weak. Okay, how can we avoid this, what I'm calling tail noise, this tail of smallish but still too large singular vectors? What we can do is instead of sketching A, so we are using linear, like these randomized sketching methods to get this error metric. Instead of sketching A, we can sketch A raised to the q with power for some reasonably large q. When you raise something to the q with power, it basically powers up its singular values. So if I plot the spectrum of A versus the spectrum of A raised to the q, and I scale them so they have like the same top singular value, A to the q has a much stronger spectral decay because I've powered it up. So its tail of singular values is much smaller. Mathematically, it means that the Frobenius norm error between A to the q and its best rank K approximation is actually small compared to its larger singular values. So if I perform sketching on A raised to the q with power, I'm going to get a good, basically good singular vectors of my matrix. This is actually exactly what power method does. So it's not how people look at power method ever. I mean, so usually you look at power method as you're applying your matrix to some vectors, and this is causing your vectors to converge to the top singular vectors of your matrix. But another way you can look at it is power method is just an iterative way of applying A to the q times some randomized set of start vectors. This is like applying a very coarse sketching method to A to the q. And if you use this denoising analysis rather than traditional convergence analysis, you can basically show some interesting gap-independent guarantees for the power method. So basically, you can show that instead of getting near optimal Frobenius norm error, you get this near optimal spectral norm error for your low-rank approximation, which is a much stronger notion of error, generally speaking. And your runtime is basically, the iteration cost is n(z(a)k), and the convergence time is log d over epsilon, where epsilon is your error parameter. And this is basically you run like approximately 1 over, you set q to basically 1 over epsilon. So there's no dependence on the matrix. It's just like a very simple runtime bound that gives you a very simple guarantee on your low rank approximation. There's been like a lot of work on this, and importantly, I think like it's really popular in the machine learning community. So there's tons of citations to these results on what's called randomized power method, which is basically power method. And it's implemented all over the place. Like a lot of people have started implementing it. It's because it's such a simple implementation. The analysis is simple and the bounds that you get are really simple, so it's easy to use. But the funny thing is that in the numerical linear algebra community, power method is not really the most popular thing. So often power method is replaced sort of by Lanczos and Krylov methods because they allow you to converge significantly faster. These are sort of polynomial acceleration methods. And so our quest was basically to close this gap. Like if this power method analysis has become so popular amongst data analysis and machine learning, can we make a Krylov analysis that sort of matches what it does? Sorry, I'm going backwards. Okay, and so the basic idea of, well, our view of Krylov methods, and this is sort of the basic idea behind Krylov methods, is that if I'm going to denoise the spectrum on a matrix by raising it to some high power, a better thing to do, instead of raising it to a high power, I can actually apply a Chebyshev polynomial to that matrix. So if you don't know Chebyshev polynomials, they literally are the polynomials that are as small as possible in some range, like 1 to 0 to 1, and then as large as possible outside of that range. So they're literally the optimal polynomials for doing denoising in the sense that I'm talking about. They depress small values and blow up large values. And they can give you like a square root acceleration. So if I needed to set my degree to 1 over epsilon in the power method, I need to set it to 1 over square root of epsilon with a Chebyshev polynomial. So if we can compute a Chebyshev polynomial of our matrix and apply a matrix sketching method to this, we would get a good low-rank approximation in terms of spectral norm. The issue is that we can't like explicitly compute this polynomial. So the actual parameters of the polynomial will depend on the spectrum of our matrix, which we don't know because we haven't done the SVD yet. So we're going to adopt the traditional strategy in numerical methods, which is that we use a Krylov subspace method. A Krylov subspace is basically I produce every single polynomial of my matrix applied to like my vectors, my random start vectors. And then I know that my Chebyshev polynomial falls within the span of this Krylov subspace. Every polynomial is just a sum of these monomials with different weightings. So I know that my Chebyshev polynomial falls in the span of this Krylov subspace. If I can somehow return the best low-rank approximation within this span, I'm going to do as well as my Chebyshev polynomial. I'm never going to have computed the Chebyshev polynomial in the first place, and I'm going to get a good low-rank approximation. So this is like the trick behind Krylov methods. It's used all over the place in the numerical computation literature. The question is, how do we get this best solution in the span of the Krylov subspace? This was what we really set out to answer. The traditional answer is to use this thing called the Rayleigh-Ritz method, which I won't go into detail, but basically the idea is you project your matrix to the Krylov subspace and you take the best low-rank approximation within that projection. Now, unfortunately, like all analysis I've ever seen of the Rayleigh-Ritz method sort of deals with the type of error that traditional sort of numerical analysis looks at, which is the distance between your singular vector and the true singular vectors. And it sort of inherently requires that you have converged to the true singular vectors for these sorts of bounds to go through. So we had to sort of take a different approach. And what we basically noticed is that the Rayleigh-Ritz method gives you a provably optimal low-rank approximation in terms of Frobenius norm for your Krylov subspace. So if I do Rayleigh-Ritz, I'm going to get the best low-rank approximation of my matrix measured in Frobenius norm that falls within my Krylov subspace. Fortunately, our entire analysis relies on Frobenius norm guarantees. We took these original Frobenius norm guarantees of the sketching methods, and we sort of made them stronger by powering up our matrix. So this optimality in terms of Frobenius norm is all we need to get our results. And it sort of gives a different analysis of Rayleigh-Ritz. It's like approaching Rayleigh-Ritz from a totally different perspective than traditionally, and you're getting a new result from approaching it from this perspective. So the upshot really quick is just that we get the first, quote, gap-independent bound for a Krylov subspace method. We basically have a number of iterations dependent on epsilon, our error parameter, rather than the spectral gap, which can be super small and which you don't have control over. And this accelerates power method by turning an epsilon into a square root of epsilon, which can be significant. There's lots of open questions here, but I'm running like low on time. So I'm just going to sort of want to survey a couple other ideas. So the upshot of this is all I want to say is that what we basically did was look at what was being done in theoretical computer science and machine learning and combine that with what had been done in numerical linear algebra. And I think there's tons of ways that that can still be done with improving lower rank approximation algorithms and getting stronger theoretical results. Let me just give one other example of this real quick. This is a paper at ICML. I guess it was presented yesterday at ICML, actually. Again, on eigenvalue computation via shift and invert preconditioning. The idea here is to basically combine another randomized method, which is stochastic gradient descent, with another classical idea from numerical linear algebra, which is like inverse iteration or shifted power method. Basically, stochastic gradient descent, or stochastic methods in general, the way I view them is you're trying to take iterative methods whose base cost is usually a matrix vector multiply, which costs the number of non-zeros in the matrix. And you're trying to replace that base cost with a vector-vector multiply. You sample one row of your matrix and you a vector-vector multiply. By accelerating the number of iterations, you can get all sorts of speed-ups. You can get better results in streaming settings, distributed settings, et cetera. So these things work really well in practice. There's lots of interesting theory. And so obviously there's an interest in using them for doing principal component analysis. There's lots of papers on this. And sort of the traditional viewpoint is that what you can do is computing the top eigenvector of a matrix or the top singular vector is a non-convex problem. But the hope is that it's simple enough that you can sort of analyze it and show that these convex optimization techniques still work. Well, what we did was instead of trying to analyze this non-convex problem, we just said, let's reduce this problem to the most popular convex problem, which is basically linear system solving. So I want to reduce getting the top eigenvector of a matrix to solving a linear system in that matrix. And this is like a classic idea in numerical linear algebra called shift and invert preconditioning. Basically, you choose a specific matrix such that when you compute the inverse of that matrix, if you apply power method, it's going to give you very fast convergence of the top eigenvector. I'm going to skip all the details of this, but the idea is basically that we then do our invert step of shift and invert preconditioning using stochastic gradient methods, basically black box. And then we're able to show speedups for computing the top eigenvector that get all sorts of trade-offs with the size of your matrix, your spectral gaps, et cetera. And I think we sort of contribute two things other than just combining the two ideas. One is that we're sort of analyzing these stochastic gradient methods specifically for use in this shift and inverted setting. Two is that these sort of methods give much looser guarantees than traditional linear system solvers. And so we have to sort of redo the analysis of shift and invert preconditioning and make it significantly more robust than you would find in a traditional analysis. So by doing this, we sort of open up this method to being used for a much broader range of solvers than what would typically be considered by people in numerical linear algebra. So that's basically, I think I'm going to cut it off there. And yeah, that's it.